We've already talked about differentiating sin and cos, so let's talk about the derivatives of the other trig functions, including the new ones that we introduced in chapter 6. So all of them are given to you here, where k is just a constant, so something like 2, 3, 4, something like that. Now, all of these are given to you in the formula booklet, so you don't have to remember them, although I would recommend that you remember the tan one, because even though it's given to you in the formula booklet, it comes up so frequently that you probably should remember it. But with all the other ones that have like quite complicated derivatives, they're given to you in the formula booklet, you don't have to remember them. Now, you may be asked to prove these derivatives, and you don't need to do it from first principles, so this makes it very easy. All you need to do is use the quotient rule, which we talked about in the previous video, so go back to that if you need a reminder. But the quotient rule allows us to differentiate fractions like u over v, and we can write tan of x as sin of x over cos of x. So therefore, we can say that sin of x is u, and then we differentiate u, du over dx, and then if you differentiate sin of x, it's cos of x, and then we call the denominator v, so v is equal to cos of x, and then dv over dx is cos x differentiated, which is minus sin of x, and then dy over dx, if you use this formula, which is also given to you in the formula booklet, it's going to be v multiplied by du over dx, which is cos x multiplied by cos of x, which is cos squared of x, minus u multiplied by dv over dx, so it's going to be sin x multiplied by minus sin of x, so it's going to be minus sin squared x, and all of this is over v squared, so it's cos squared of x, and these two minuses cancel out to give a plus, and remember the identity that sin squared x plus cos squared of x is equivalent to 1, so this up here is just equivalent to 1, and then 1 over cos squared of x, which we talked about in chapter 6, is sec squared of x. So dy over dx is sec squared of x. And then the other three are the exact same. So for example, for cosec of x, we rewrite it as 1 over sin x, and then u is going to be equal to 1, and if you differentiate 1 or any constant, it becomes 0, and then v is going to be the sin x, and then dy over dx is going to be, so as du over dx is 0, this term here isn't going to exist because we're multiplying by 0. So in the numerator, it's just the minus u dv over dx, which is minus cos of x, and this is over v squared, and we can split this up into 1 over sin x multiplied by cos x over sin x, which is equal to cosec x here and cos of x here, and then that's dy over dx. I'm not going to do the other two because it's literally the exact same thing. You just use the quotient rule and rewrite whatever the trig function is in terms of sin and cos. So here's some examples of when we need to use these trig derivatives. So for the first one, this one's actually mentioned on the specification. So we need to use the chain rule for this one because we have a function within another function. If you need a reminder of when we use the chain rule and how to use it, go back to the video in this chapter on the chain rule. But it's a function within another function. It might be a bit clearer to see this if we write it in this format here. The inner function is this tan 2x, and the outer function is this power of 2 here. So we need to use the chain rule. Remember, the chain rule is the inner function differentiated multiplied by the outer function differentiated. So dy over dx is going to be equal to the inner function differentiated, so this tan 2x differentiated, and remember in the formula booklet it tells you that dy over dx of tan of kx is this here, so we just need to replace the k's with 2's, so it's going to be 2 sec squared of 2x, so that's the tan 2x differentiated, and this is multiplied by the outer function differentiated, which is this power of 2 here. So when you have something to the power of 2, when you differentiate it, the 2 comes down as the coefficient, and then we still have the same inner function here, which we don't change. Again, go back to the chain rule video if you need a reminder of how this works, and this will be to the power of 1 now, but we don't really need to write this. So this is dy over dx, and if you simplify this, 2 times 2 is 4, so dy over dx is going to be 4 sec squared of 2x tan of 2x. And then for the second example, we have y is equal to e to the power of 3x multiplied by cosec of x. We need to differentiate this. And because we have two functions multiplied together, we need to use the product rule. So again, go back to the product rule video if you need a reminder of how this works. But we call one of the functions u, so let's call e to the power of 3xu, and then we do du over dx is going to be, and if you differentiate e to the power of something x, this constant will come down as the coefficient, so it's going to be 3e to the power of 3x like this, and then we call the other function v, so v is equal to cosec of x, and if you differentiate cosec of x, this is given to you in the formula booklet with k just being 1 here, so we don't need to write the the one part here. dv over dx is going to be minus cosec of x cos of x, like this here. So dy over dx is going to be u multiplied by dv over dx, so it's going to be minus e to the power of 3x cosec of x cos of x, and this is plus v multiplied by du over dx, which is going to be 3e to the power of 3x cosec of x. You could factorize this because you have e to the power of 3x cosec of x common in both terms to simplify it slightly, but you don't need to. So here's a couple more examples here. So for this one here, we have y is equal to 4 sec of x cosec of x. So this is two functions multiplied together, so we're going to use the product rule. So if we say that u is equal to this 4 sec of x part here, then du over dx is equal to, so remember when you differentiate something with a coefficient in front of it, this coefficient here will just come down like this here, and then we differentiate sec of x, and if you differentiate sec of x, you can look in the formula booklet, it gives you the derivative is equal to sec x tan of x, like this here. And then if we call the cosec of x here, then dv over dx is equal to, and if you differentiate cosec of x, you get minus cosec x cos of x, like this here. So dy over dx is equal to u multiplied by dv over dx, which is going to be this here, and then plus v multiplied by du over dx, which is going to be this here, like this. And we can do some simplifying on this if we write it in the sin and cos formats for the sec, cosec, cot and tan. So if we write this in this format here, with sec being 1 over cos, cosec being 1 over sin, and cot being cos over sin, and writing this format here as the same, with tan being sin over cos, like this here. This cos can cancel out with this cos here, and then this sin can cancel out with this sin here. So therefore we're just going to be left with sin x multiplied by sin x here, so it's going to be sin squared x in the denominator here, and then it's going to be cos x multiplied by cos x here, so it's going to be cos squared x in the denominator here. And we can write this here, we brought this 4 into the numerator here, we can write this as minus 4 cosec squared of x, and then we can write this here as plus 4 sec squared of x. So this is the simplified version of dy over dx. And then for the fourth one, we have y is equal to 3 cot of x to the power of 3 plus 1. So for this one, we need to use the chain rule, because we have the inner function here as x to the power of 3 plus 1, the outer function as this cot here. So dy over dx is going to be equal to, so this 3 coefficient is still going to be here, so it's going to be 3 multiplied by, and then it's going to be the inner function differentiated, so this x to the power of 3 plus 1 differentiated. X to the power of 3 differentiated is 3x squared, and then this plus 1, when you differentiate it, it's just 0, so we don't write it. So that's the inner function differentiated, and it's going to be multiplied by the outer function differentiated. So it's this cot differentiated, and in the formula booklet, this is the derivative of cot, so it's going to be minus cosec squared of, and the inner function still, of x to the power of 3 plus 1, like this here. You might be wondering if there's like a k involved here, and if anything goes to the front, like the coefficient. There isn't, because we treat this whole thing as the inner function, and when we treat this thing as the inner function, when we're doing the outer function, it's almost as if you kind of like group this x to the power of 3 plus 1 as kind of like a whole x when we're talking about it here, and we don't really have a k. So this whole thing is grouped together in terms of like the x when we're differentiating the cot, like this here. And we can simplify this because we've got 3 times 3 and then the negative sign, so it's going to be minus 9x squared cosec squared of x to the power of 3 plus 1. Now, I've talked about this in all of the videos in this chapter so far. For a more detailed explanation on this, go back to the first video in this chapter titled Differentiating Sin, Cos, Exponentials and Logarithms. But I want to mention it here quickly as well because I think it's useful. There's a really good way to check your answers, in my opinion, to differentiation questions in an exam by using your calculator. So let's show how it works by using this example here that we just did. So on your calculator, if you press Shift and then this integration symbol here, you get this differentiation term. And if you put in the y value that the question wants you to differentiate, so in this case it's the 3 cot of x to the power of 3 plus 1, there's no cot function on your calculator, so you'll have to use the tan format of 3 over tan x to the power of 3 plus 1. It's the same thing, we've just written it in the 1 over tan format instead. And then if you put in a random value for the x is equal part, so for example, let's just say x is equal to 5, and then press equals on your calculator gives out a value of minus 2066.23. What this value is your calculator differentiating this expression here and then subbing in x is equal to 5 into the resulting derivative. So why is this useful? Because we can sub in the same x value, so x is equal to 5, into this derivative here that we figured out previously using algebra and using our differentiation methods. So that's what I've done down here. I've subbed in x is equal to 5 into this expression. Again, there's no cosec function on your calculator, so I've written it in the 1 over sin format, but it's the same thing, it works. And if you put this into your calculator, remember to use the radians mode because we're doing differentiation. We never do differentiation in degrees. And if you press equals, your calculator also gives out a value of minus 2066.23. So this value here is given by your calculator differentiating this expression itself and then subbing in x is equal to 5. And this value is given out by us subbing x is equal to 5 into the derivative that we figured out ourselves earlier. And because these two values are the same, this tells us that this expression here that we figured out, this derivative, is correct. We did all the working out correctly and we didn't make any errors because these two numbers are the same. Now, we can't just use this to solve the original question on its by itself because one, that's not how it works. It doesn't give out this expression here, and two, even if it did, the examiners won't allow it because obviously you haven't actually done any work. You've just plugged it into your calculator. But what this is really, really good at is making sure that you haven't made any like mathematical errors in your working out and you've done all the working out correctly and you've got the answer correct. You also need to be aware of the derivatives of the inverse trig functions Arcsin, Arccos and Arctan, which are given here. These aren't given to you in the formula booklet, which is quite harsh in my opinion, so you're going to have to remember them. Now, you may be asked to prove these derivatives for these inverse functions. So let's show how this works, starting with the arcsin, and we need to prove that dy over dx is equal to 1 over the square root of 1 minus x squared. Well, let's start with what we know, that y is equal to the arcsin of x. And if y is equal to the arcsin of x, by definition, x is equal to sin y. That's just the definition of arcsin, that's just how it works. And this here, we can differentiate using dx over dy. We've basically just changed the roles of the x and the y, such as that this y is now basically going to act like an x. We can basically think of this as sin x. So when we differentiate this sin y, when this y is on the bottom, this sin y, when you differentiate it, is going to be cos y. Okay, so we've got dx over dy is equal to cos y, and this dx over dy, we've met this before. We met this in the chain rule video, and we talked about the formula that dy over dx is equal to 1 divided by dx over dy. You need to remember this formula. Again, go back to the chain rule video if you need a reminder of it. The best way to remember it, in my opinion, is that it's 1 divided by dx over dy, and it sort of works like a fraction, with this fraction flipping when you do the 1 divided by. That's not actually how it works in terms of the maths of it, but it's a good way of remembering it. That's the way I remember it. So therefore dy over dx is going to be 1 divided by dx over dy, which is going to be 1 divided by this cos y. Okay, so we have this here. And if you remember the identity that we use all the time, that sin squared y plus cos squared y is equivalent to 1. Well, if we move the sin squared y onto the other side, we get cos squared y is equivalent to 1 minus sin squared y. And if we take the square root of both sides, we get that cos y is equivalent to the square root of 1 minus sin squared y. We have cos y here, so we can make this substitution for the square root of 1 minus sin squared y like we have here. And what's key with this is that x is equal to sin y. So we can make the substitution here for sin y for x, and that's what we've done here. So now it's 1 over the square root of 1 minus x squared instead of sin y. And this is what's required, that dy over dx is equal to 1 over the square root of 1 minus x squared, and that's how you do it. Now, these are quite long, and they kind of do look a bit scary with kind of the dx over the dy and having to make the substitution kind of with the x and the y here. But I kind of think if you go through it slowly, I don't think it's that bad. And the proof for Arccos is literally the exact same thing. The minus sign just comes from the fact that when you differentiate cos y, it becomes minus sin y instead. And then this is the arctan proof. Again, it's the exact same thing, except this time we use the identity of 1 plus tan squared y is equivalent to sec squared y that we learned in chapter 6, and this gives you this answer instead. So here's some examples of some derivatives involving the inverse trig functions. So for the first one, we have y is equal to the arcsin of 2x. So we're going to have to use the chain rule, with the inner function being 2x and the outer function being the arcsin. So dy over dx is going to be the inner function differentiated, which is the 2x differentiated, which is going to be 2. And this is multiplied by the outer function differentiated, which is going to be the arcsin differentiated, which is going to be the 1 over the square root of 1 minus x squared. But remember, when you differentiate the outer function, you need to incorporate the inner function. So rather than being the x, it's going to be 2x here. We can simplify this. This 2 is going to go into the numerator. And then remember, this 2 is also going to be in the squared brackets. This whole thing is sort of the x over here. And then 2x squared is going to be 4x squared, like this here. So for the second one, we have y is equal to the arccos of x squared. So again, we're going to have to use the chain rule, with the inner function being the x squared and the outer function being the arccos. So dy over dx is going to be the inner function differentiated, so the x squared differentiated, which is going to be 2x, and this is multiplied by the outer function differentiated, which is the arccos differentiated, which is going to be the 1 over the square root of 1 minus x squared. But remember that we incorporate, when we use the chain rule and we differentiate the outer function, we incorporate the inner function in this. So instead of x, it's going to be the x squared here instead. And we can simplify this, where the 2x is going to go into the numerator, and then x squared squared is going to be x to the power of 4. So dy over dx is going to be this here. And then for the third one, we have y is equal to 4x multiplied by arctan of x. So as we have two functions multiplied together, we need to use the product rule. So let's say that u is equal to 4x, therefore du over dx is going to be 4x differentiated, which is 4. And then we can say that v is equal to the other function, which is arctan of x, and dv over dx is equal to arctan differentiated, which is 1 over 1 plus x squared. So therefore dy over dx is equal to u multiplied by dv over dx, which is 4x over 1 plus x squared, plus v multiplied by du over dx, which is 4 arctan of x. So now we're going to go through some past exam questions. So here's an example of this, where we're told a curve has the equation y is equal to e to the power of 2x multiplied by tan of x. And we need to show that the turning points occur when tan of x is equal to minus 1. Now, we've talked about this before. Turning points exist when dy over dx is equal to 0. So what we need to do, we need to find dy over dx, equal it to 0, and then find the x coordinates and show that this is when tan of x is equal to minus 1. So we need to find dy over dx to start off with, and we can find it using this. So we're going to use the product rule because we have two functions multiplied together. So let's say that u is equal to the first function, which is e to the power of 2x. Therefore du over dx is equal to, and if you differentiate e to the power of 2x, you get 2e to the power of 2x. And then if we say v is equal to tan of x, dv over dx is equal to, and if you differentiate tan of x, we talked about before, you get sec squared x. So therefore dy over dx is going to be u multiplied by dv over dx, which is going to be e to the power of 2x sec squared of x, and this is going to be plus v multiplied by du over dx, which is going to be 2e to the power of 2x tan of x. Okay, so we want to equal this to 0 to find the turning point, so that's what I've done here. And we've got e to the power of 2x present in both the terms, and as e to the power of 2x can't be equal to 0, you can't have e to the power of something be equal to 0. We can divide everything by e to the power of 2x, like this here. So we're just left with sec squared of x plus 2 tan of x is equal to 0. And this is a trigonometric quadratic. Now, we talked about how to solve these in chapter 6 in the trigonometric identities and equations video. So go back to that if you need a reminder. But the key to solving trigonometric quadratics is we can't have more than one trigonometric function present. And at the moment we have two. We have sec and we have tan. We only want one of these present. So we have to get rid of one of them. one of them. And the way that we can do this is we can use the identity that 1 plus tan squared of x is equivalent to sec squared of x, and we can substitute out this sec squared of x for 1 plus tan squared of x, and that means we'll only be left with tan of x. So that's what I've done here. We've substituted out the sec squared of x of 1 plus tan squared of x. And this is a quadratic only involving tan. I've rewritten it the order just so it's a bit more familiar in the traditional x squared plus x plus constant form like this. Now you could just solve it like this, but if you want to make a substitution to make it just a bit more familiar, you can. So if you say something like a is equal to tan of x, we can rewrite this as a squared plus 2a plus 1 is equal to 0. And then hopefully you can see with this quadratic that this is really easy to factorise. We can just factorise this as a plus 1 is equal to 0, which is obviously a plus 1 squared is equal to 0, and then we can square root both sides, so it's a plus 1 is equal to 0, and therefore a is equal to minus 1, and as a is the substitution that we made for tan of x is equal to minus 1, which is what's required. And then for part B, we need to find the equation of the tangent at the point where x is equal to 0. So if you recall back to year 1 of chapter 5, the equation of a straight line, in order to find the equation of a straight line, we need two things. We need the gradient and we need a coordinate on the line. Well, we can figure out the gradient because if you think about back again to year 1 differentiation on the tangent video, the gradient of the tangent is going to be the gradient at the point at which it intercepts. So it's going to be the gradient where x is equal to 0. And as we have dy over dx, all we need to do is sub in x is equal to 0 in order to find the gradient at x is equal to 0. So that's what I've done down here, and if you put this into a calculator or just figure it out, you get that this is 1. So therefore the gradient at the point x is equal to 0, and therefore the gradient of the tangent is going to be 1. And we also need a coordinate on the tangent, and we know an x coordinate, we know x is equal to 0, but we don't know the y coordinate, but obviously we can easily figure this out by using the equation for y up here and subbing in x is equal to 0, which I've done here. And again, if you figure this out, y is equal to 0. So a coordinate on the line is 0, 0. And then if you plug the values into this equation, or you've just figured it out already, it's going to be y minus, and then the y coordinate is 0. And this is equal to the gradient, which is 1. And then x minus 0, which is the x coordinate. And this here is just y is equal to x. So this is the equation of the tangent. So here's another past exam question. So we're given this curve here and we're told that it has the equation y is equal to 2x minus 1 tan of x, and we are told that it has the minimum at the point P, so it has this minimum here, and at this minimum the x coordinate is k, and we need to show that k satisfies this equation here. So this is a minimum and it's a turning point. Remember, as we talked about before, that at turning points and stationary points, dy over dx is equal to 0. So what we need to do, we need to find dy over dx, set it equal to 0, and then show that we can satisfy this equation here. So firstly, we need to find dy over dx, so we need to differentiate this, and we're going to do this using the product rule because we have two functions multiplied together. So if we say that u is equal to the 2x minus 1, we can then say that du over dx is equal to, and then if we differentiate the 2x, it becomes 2. If you differentiate minus 1, it just goes away. So du over dx is equal to 2, and that means that v is equal to the other function, which is the tan of 2x. So therefore dv over dx is equal to, and then remember, if you look in the formula booklet, the if y is equal to tan of kx, and then dy over dx is equal to this. So therefore dv over dx when k is equal to 2 is going to be 2 sec squared of 2x like this. So therefore dy over dx is going to be u multiplied by dv over dx, which is going to be 2x minus 1 sec squared of 2 of x, and this is going to be plus v multiplied by du over dx, which is going to be 2 tan of 2 of x. And then we're going to set this equal to 0 for this minimum turning point, but we're also told that at this minimum point the x coordinate is k, so we can equal this here to 0 like I've done down here, but we also know that the x coordinate is k, so we can replace x with k. And now all we need to do is just rewrite this equation into this format here. So if we rewrite the sec and the tan into their sin and cos formats like I've done here, you can see that in both of the denominators of the terms we have this cos 2k. So what we can do is we can get rid of it for both of them by multiplying everything by cos squared of 2k. This will cancel out this denominator here, and it will cancel out this denominator here, but it will leave this numerator now multiplied by another, because it's to the power of 2, by another cos 2k, like this here. And if we expand this bracket here, we get it's 4k minus 2. I'm just going to slightly rewrite this equation, rearrange the terms into this here. And now you can see that this equation and this equation are very similar. We've got the 4k minus 2 in both of them. The only difference is that in this one we've got sin of 4k, and in this one we've got 2 sin of 2k cos of 2k. So this is a sign that we're going to have to use the double angle formula to get from 2k to 4k. So the double angle formula, as we've covered in chapter 7, is this here, and this is already in the format that we need it to be, that 2 sin of 2k cos of 2k is equal to sin of 4k. So we just make the substitution and we get the 4k plus sin of 4k minus 2 is equal to 0, which is what's required. Now, just very finally, a question that they sometimes like to ask is one where you need to find dx over dy in terms of y, and then find dy over dx in terms of x. And the way that you do this is you use trig identities that we've talked about in previous chapters. So let's do a past exam question of this type to show what I mean by this. Now, we've actually already done this technique when we proved the derivatives of the inverse trig functions. But for this question, we're told that if x is equal to sec of 2y, firstly, find dx over dy in terms of y. Now, remember, dx over dy is the opposite of dy over dx. Basically, the x and the y roles are swapped around, so the y basically becomes the x, and you can think about this like sec of 2x, like this here. And remember, you're given the in the formula booklet, you're given that if y is equal to sec of kx, then dy over dx is equal to this here. So if we differentiate this, it's just going to be the k being equal to the 2 here, and the y swap for the x. So dx over dy of this here is going to be 2 sec of 2y tan of 2y. And then for the next part, we need to find dy over dx in terms of x. Now, we've already talked about in this video that the relationship between dy over dx and dx over dy is this here. And as we have an equation for dx over dy, we can find dy over dx as 1 divided by this here, so 1 over 2 sec of 2y tan of 2 of y. So we found dy over dx, but the issue is we need to find it in terms of x, and at the moment we have it in terms of y. So how do we write this in terms of x? Well, we need to use the first equation up here, that x is equal to sec of 2y. And you can see that this sec of 2y, we actually have this in this equation here. So we can substitute out this sec of 2y for x, like this here, where dy over dx is now equal to 1 over 2x tan of 2y. So now we just need to replace this tan of 2y with an x. And the way that we're going to do this is by using the identity that 1 plus tan squared of x is equivalent to sec squared of x. And in terms of the variables that we're using, it's going to be 1 plus tan squared of 2y is equivalent to sec squared of 2y. And as we know that sec of 2y is equal to x, sec squared of 2y is going to be equal to x squared. So 1 plus tan squared of 2y is equivalent to x squared. Move the 1 onto the other side, so it's tan squared of 2y is equivalent to x squared minus 1. And then take the square root of both sides, so that tan of 2y is equivalent to the square root of x squared minus 1. And then we can just replace this tan of 2 of y with this square root of x squared minus 1. So just dy over dx is written here in terms of x, and this is the final answer. So here's a couple of past exam questions for you to have a go at on this topic. This is kind of the biggest I could get it by getting both of them on the screen. If it's a bit too small for you, when I go through each individual question, I'll make the section bigger so it's easier to see. But for here, pause the video, have a go, and I'll go through the answers in about 5 seconds. So for question 1 part A, I'm not going to go through this because I've already been through it in this video, and obviously it's the exact same thing, but I think it's quite good for you to have a go at this and see if you can either figure it out or remember it. So here's how you do it here. So for part B, we're told that if y is equal to e to the power of 2x multiplied by sec 3 of x, then we need to find dy over dx. So we're going to use the product rule here because we have two functions multiplied together. So if we say that u is equal to e to the power of 2x, then du over dx is going to be, so this 2 is going to come down as the coefficient, so it's going to be 2e to the power of 2x, and then we say v is equal to the other function, which is sec of 3x, then dv over dx is equal to, so remember in the formula booklet it tells you what happens when you differentiate sec of kx, so dv over dx is going to be 3 sec 3x tan of 3x. So therefore dy over dx is going to be u multiplied by dv over dx, which is going to be 3e to the power of 2x sec of 3 of x tan of 3 of x, and this is going to be plus v multiplied by du over dx, which is going to be 2e to the power of 2x sec of 3x, and it's fine to leave it in this form here. So for part C, we're told the curve with the equation that we figured out dy over dx for in part B has a turning point in this interval at AB, and we need to find what AB is. So remember, the turning point exists, we've talked about this before, a turning point exists when dy over dx is equal to 0, and as we figured out dy over dx in part B, we can set this equal to 0, and then we just need to find x. So we have e to the power of 2x common in both the terms, and as e to the power of 2x cannot be equal to 0, you can't have e to the power of something equal to 0. Therefore we can divide everything by e to the power of 2x to just leave us with this here. And you can see that we have sec of 3x common in both terms, so we can factorize this out such as it's sec 3x and then 3 tan of 3x plus 2 is equal to 0. So that means that either sec of 3 of x is equal to 0 or 3 tan of 3x plus 2 is equal to 0. So let's focus on the sec of 3x being equal to 0. So remember, sec of 3 of x can be written as 1 over cos of 3 of x, but you can't have 1 divided by something equal to 0. That's just not possible. So therefore this here isn't possible, so therefore sec of 3 of x cannot be equal to 0. So this isn't a solution. So therefore the only possible solution is when 3 tan of 3 of x plus 2 is equal to 0. So now we just need to solve this equation here. So firstly we move this 2 onto the other side to get this, and if we divide both sides by 3, we get that tan of 3 of x is equal to minus 2 over 3. So this is a trigonometric equation, and as this interval has pi in it, we need to find x in terms of radians. Now we talked about how to do this back in year 2 of chapter 5 in the video trigonometric equations involving radians. So go back to that video if you need a reminder. But firstly we need to adjust this interval here because we have it in terms of 3x, but at the moment it's in terms of x, so therefore we need to multiply everything here by 3 such that we get this here, and the new interval is between minus pi over 2 and pi over 2. So if we take the inverse tan of minus 2 over 3 and put it into our calculator, remember that we need to put our calculator in the radians mode, we get a value of minus 0.588, and this does lie in this interval here, and if you draw a quick tan graph in this interval you can see that this is the only value for tan is equal to minus 2 over 3, so therefore 3x is equal to minus 0.588, and then x is equal to, if you divide both sides by 3, to minus 0.196, and this is the only solution to x in this interval. Now it says the minimum turning point, so you might be asking yourself that you might need to prove that it's the minimum and not a maximum or something like that, but because this is the only value of x in this interval in which dy over dx is equal to 0, therefore this is the only turning point, so therefore it has to be this minimum turning point that they're talking about. So this is the x value for the turning point, and to find the y value of the turning point we just plug x into the equation for y, which is what I've done here. So it's going to be y is equal to e to the power of 2 of minus 0.196 multiplied by sec of 3 of minus 0.196. You don't have a sec function on a calculator, so you have to write this in the 1 over cos variation like this here, and if you put this into your calculator, again with your calculator in radians, you get a value of 0.812. So therefore the turning point, these values of a and b, the value of a is the x coordinate, which is the minus 0.196, and the b is the y coordinate, which is the 0.812. So for question 2, we have this equation here, and for part A, we need to find the value of dy over dx at the origin. So as this equation at the moment, the subject is x, the easiest thing to do is to find dx over dy and then use the relationship that we know to find dy over dx, like this here. So if we find dx over dy. So we need to differentiate this. Remember, when you do dx over dy, the y is kind of the x now. So if we differentiate this 4 sin of 2y, it's going to be, so this 4 coefficient is still going to be here. And this is going to be multiplied by sin of 2y differentiated. And remember that if you differentiate sin of kx, or in this case sin of ky, the k will come to the front. So this 2 here is going to come to the front, and then if you differentiate sin, it becomes cos, and then it's still going to be 2y like this. So when you differentiate sin of 2y, it becomes 2 cos of 2y, and we simplify this because 4 times 2 is 8, so dx over dy is equal to 8 cos of 2y, and because dy over dx is equal to 1 divided by dx over dy, we can write dy over dx as 1 over 8 cos of 2y. So we need to find the value of dy over dx at the origin. Remember, the origin is 0, 0, so that means that y is going to be equal to 0, so all we just need to do is sub in y is equal to 0 into dy over dx, and if you just figure this out or put it into your calculator, you get a value of 1 over 8. So that's the value of dy over dx at the origin. So for part BI, it says we need to use small angle approximations of sin of 2y to find an equation linking x and y for points close to the origin. And the reason that we can use small angle approximations here is because for points close to the origin, so remember the origin is 0, 0. So for points that are close to the origin, that means that the x and the y value, when they're close to the origin, are also going to be approximately equal to 0 as they're close to the origin. So therefore x and y are small, so therefore specifically as y is small, we can use the small angle approximation for sin of 2y, as this y value is small enough. So remember, these small angle approximations are given to you in the formula booklet, that for sin, that sin of theta is approximately equal to theta. So for sin of 2y is approximately equal to 2y. So for this equation here, x is equal to 4 sin of 2y, we can make the substitution for sin of 2y is just 2y. So x is going to be equal to the 4 multiplied by now 2y. So x is going to be equal to 8y. So this is the equation linking x and y. And then for the second part of B, I think this is just something you have to spot. The easiest way to see it is if you move this 8 onto the other side, such that it becomes y is equal to 1 over 8x, like this here. So the value we got in A for dy over dx at the origin was 1 over 8, and if you look at this line here, you can see that the gradient of this line is 1 over 8, as it's the form y is equal to k of x. So therefore the value of A, which is 1 over 8, is the gradient of this line here in the first part of B. So for part C, this is nothing to do with part B and these small angle approximations like this up here. This is more related to part A and this equation up here. What we basically need to show is that dy over dx can be written in this form here. Now you might recall that in part A, we found an equation for dy over dx, which we got up here, but now we need to write it in terms of x, where the dy over dx equation that we got in part A is written in terms of y. This is similar to the question format that I talked about previously, in which we need to find dy over dx in terms of x, but at the moment it's in terms of y, and we need to use trig identities in order to rewrite this in terms of x. So how do we do this? Well, we have this equation up here linking x and y, and if we divide both sides by 4, we get that x over 4 is equal to sin of 2y. So we have this equation linking x and y, but the problem is we don't need sin here, we need cos here in order to make this substitution. So this gives us a clue in terms of the trig identity that we need to use. We need to relate sin and we need to relate cos. So therefore we're going to use the trig identity that sin squared x plus cos squared x is equivalent to 1, and as we've got 2y here, it's going to be that sin squared of 2y plus cos squared of 2y is equivalent to 1. And as x over 4 is equal to sin of 2y, sin squared of 2y is going to be x over 4 to the power of 2. So now we've got this equation here. The x over 4 to the power of 2 plus cos squared of 2y is equal to 1. And now we can rearrange this in order to make cos of 2y the subject. So we can make the substitution here for x. So firstly, we can expand the brackets here with this squared, so it's going to become x squared over 16 is equal to cos squared of 2y. We can move this x squared over 16 onto the other side to get the cos squared of 2y is equal to 1 minus x squared over 16. If we combine this bracket together, so this would become, if we rewrite 1 as 16 over 16 minus x squared over 16, so these denominators are the same, we can get that cos squared of 2y is equal to 16 minus x squared over 16. And now we can square root both sides such that cos of 2y is equal to square root of 16 minus x squared over 16. And the square root of 16 is just 4, so therefore we can write cos of 2y as the square root of 16 minus x squared over 4. So now we have the equation that cos of 2y is equal to the square root of 16 minus x squared over 4. So now we can make the substitution for cos of 2y, so dy over dx is equal to 1 over 8, and we replace the cos of 2y with this here. We do some simplifying in order to get into this form here. This 8 and this 4 can cancel down, so this 4 will go away and this 8 will now just be 2, like this here, which will leave us with 1 over 2 and then the square root of 16 minus x squared. And this here is in the form that we need it of 1 over a, the square root of b minus x squared, where a is equal to 2 and b is equal to 16.